Now let's consider a macroscopic system whose macrostate is specified by its absolute temperature T and a set of macroscopic parameters Y, which can be average pressure or volume. So we have a macroscopic system which has a macrostate in a macrostate which is specified by absolute temperature T and a set of external parameters, macroscopic parameters, set of macroscopic parameters Y. So Y can be, for example, average pressure or volume, etc. Now, the heat capacity of the system is defined in the following way. The heat capacity of the system is defined with the following equation. We denote heat capacity with capital letter C, subscript Y, so that is going to indicate that Y is kept constant. So this is defined as infinitesimal amount of heat absorbed for infinitesimal temperature change under the conditions that Y is kept constant. So all parameters Y kept constant. This value of the heat capacity, Cy, will change depending on what the absolute temperature of the system is and what the value of Y is. And it's going to be given calories per Kelvin. So that's the unit, because we have heat divided by temperature, absolute temperature. That's calories per Kelvin. Now, if we specify the heat capacity per a quantity of the substance, we call it specific heat. For example, the heat capacity per mole. It's also known as molar specific heat or specific heat per mole. This is just going to be the heat capacity of the substance divided by the number of moles, and we show it with a lowercase letter c. C sub y is 1 over the number of moles times heat capacity. It is 1 over the number of moles times infinitesimal amount of heat absorbed for a small temperature change under the condition that parameters y are kept constant. So this will be in units calories per Kelvin per mole. And once again, the specific heat is temperature dependent and does also depend on the value of y. So just like what we see in the heat capacity. The heat capacity per gram, so we can also give it in terms of per mass. So the heat capacity per gram, or we can call it specific heat per gram, this will be similar to molar specific heat, except that we're now dividing. So let's show it with Cy prime in order to indicate that it's different specific heat, is 1 over the mass multiplied by the heat capacity, which is 1 over m d bar q dt with y parameters kept constant. Now, since we have this relationship between d bar q and the heat capacity, we also know from the first law of thermodynamics that under the condition that the external parameters are kept constant, there will be no work done on the system, and the amount of heat that we absorbed will basically reflect as a change in the total mean energy of the system. So basically we can also write the heat capacity in terms of a change in the mean energy. So if we have all the external parameters which we denote by x are kept constant, that means the system has a thermal interaction and the bar W will be 0. So that's going to imply a change in the mean internal energy of the system is d bar Q, because d bar W is 0. For example, a constant volume gas, right? So we will have then the heat capacity given by d bar Q divided by dt derivative for x kept constant, external parameters kept constant, or the derivative of E bar with respect to temperature with x kept constant, so that we have no work done on the system. And regarding the value of Cx, I would like to remind you that we had a discussion which showed us that, so reminder, the temperature varies with energy. Increasing energy means increasing temperature, so that's positive. That's because the kT was the mean energy above the ground state energy per degree of freedom. So that's also going to imply del E bar del T is always going to be a positive value. So this came from the fact that we have number of accessible states varying as E minus E0 to the power number of degrees of freedom, and we have beta, which is del ln omega del E, varying as F over E minus E0, and the temperature comes into play as temperature is equal to K beta to minus 1. So del T del E basically comes from 1 over K the derivative with respect to beta minus 1 over beta square del beta del E, and that is basically minus 1 over k beta square multiplied by minus f over E minus E0 square. So this is f divided by k beta square multiplied by E minus E0 times 1 over E minus E0. So you have two squares here, and f divided by E minus E0 is beta, so you would have this is beta 1 over k beta 1 over E minus E0. Beta is 1 over kT, so it is temperature divided by E minus E0. So at the equilibrium point, this would be temperature divided by E bar minus E0. But since you have two squares here and a positive value here, this is always positive. So the conclusion is that the heat capacity of a substance should be always positive. The specific heat for water is 1 calorie per gram degree Celsius. That's specific heat per gram, which can be also written as 4.18 joules per gram degree Celsius. And for also a monatomic gas, remember we calculated its mean energy using the canonical distribution. We found that the mean energy per molecule was 3 over 2 kT, and the total mean energy was 3 over 2 nkt, which is also equal to 3 over 2 nu RT, where R is Boltzmann constant K multiplied by Avogadro's number. So we find that the molar specific heat for this case will be equal to del E bar del T under constant volume. So the molar specific heat you would find for constant volume case, which is what you need because d bar W is minus PdV, remember. So this has to be 0. So if V is 0, this is going to be 0, or delta V is 0. In this case, we find that Cv is equal to 3 over 2 R, because it's the molar specific heat. We take the derivative with respect to temperature and multiply it with 1 over the number of moles. So the molar specific heat for a monatomic gas is 3 over 2 R. The specific heat of water per gram is 1 calorie per gram degree Celsius, or 4.18 joules per gram degrees Celsius. So we can give these as examples of specific heat. So let's recap what we said. We have a macroscopic system in a macro state at absolute temperature T. It has a set of macroscopic parameters Y. This could be mean pressure or volume. The heat capacity is defined as the amount of heat it will absorb per temperature change, given that all parameters are kept constant. And the heat capacity per mole is specific heat per mole, or molar specific heat per gram is specific heat per gram. And when all external parameters are kept constant so that the work done on the system is 0, d bar Q is equal to dE bar. In that case, the heat capacity is the derivative of the mean energy of the system with respect to temperature, and the temperature derivative with respect to mean energy, or the reverse, is always positive. It's always a positive value. And examples for specific heat we gave for water 1 calorie per gram degree Celsius, and then for a monatomic gas we have the molar specific heat, specific heat here. It is 3 over 2R. Why? Because using canonical distribution we found in the previous videos that epsilon bar is 3 over 2 kT, mean energy per molecule. Total mean energy was 3 over 2 N kT, and with N being the number of moles times Avogadro's constant, so this N is Avogadro's constant times number of moles, you can see that Na times Boltzmann constant is a universal gas constant, and therefore we have 3 over 2 nu RT, and for molar specific heat we have 3 over 2 R as our